For decades, Venus has hidden behind an impenetrable veil, concealing secrets that would make our understanding of Earth seem like child's play. It's our closest planetary neighbour, so close you can sometimes see it shining brighter than any star in our sky. Yet until now, we've known less about Venus's surface than we know about galaxies billions of light years away. NASA has finally pierced that veil, and what they've discovered will fundamentally change how we think about planets, life, and our own world's fragile existence. What you're about to learn isn't just about another planet. It's about understanding why Earth became a paradise, while our twin became hell. Let's begin. Venus has always been humanity's beautiful mystery. Ancient civilizations worshipped it as both the morning and evening star, not realizing they were seeing the same object. The Romans named it after their goddess of love and beauty because of its brilliant, serene appearance in our sky. But that serene beauty conceals the most hostile environment in our solar system. For most of human history, Venus remained an enigma wrapped in clouds. Early astronomers could see it was roughly Earth's size, about 7,500 miles in diameter, compared to Earth's 7,900 miles. They observed its phases, like a mini-moon waxing and crescent, but its surface remained completely invisible, hidden beneath clouds that reflect so much sunlight that Venus outshines everything in our night sky except the moon. The first breakthrough came in the 1960s, when radio telescopes began bouncing radar signals off Venus's cloud tops. These early radar maps revealed something shocking. Venus rotates backward compared to most planets in our solar system, and it does so incredibly slowly. One Venusian day lasts 243 Earth days, which is actually longer than Venus's year of 225 Earth days. Imagine living on a world where the sun rises in the west, sets in the east, and takes 4 months to cross the sky. But radar could only tell us about the cloud tops and give us crude elevation maps of the surface. We still couldn't see Venus. We couldn't understand its geology, its weather, or why it became so radically different from Earth despite being nearly identical in size and composition. The Soviet Union's Venera program provided our first glimpses of the surface in the 1970s and 1980s. These hardy probes descended through Venus's atmosphere and managed to survive on the surface just long enough to transmit a handful of images before being crushed and melted by the extreme conditions. Those grainy photos showed rocky plains, strewn with sharp fragments under an eerie orange sky. But each lander survived less than 2 hours. Venus destroyed them before they could tell us much. Since then, Venus has remained largely overlooked. NASA and other space agencies focused on Mars, the outer planets, and deep space exploration. Venus was too hostile, too challenging, too dangerous to justify the cost and risk. For decades, our understanding of Earth's closest neighbour remained frozen in time, based on data from the 1980s Soviet technology. That changed when NASA's advanced imaging systems, new orbital missions, and revolutionary analysis techniques finally gave us the capability to see Venus as it actually is. And what they found is nothing short of extraordinary. To understand what NASA discovered, you first need to comprehend just how hostile Venus truly is. This isn't Mars, where temperatures are cold but survivable with the right equipment. This isn't even close to any environment on Earth. Venus is a glimpse into planetary hell. The surface temperature on Venus averages 872 degrees Fahrenheit. That's 467 degrees Celsius. This is hot enough to melt lead, zinc, and many other metals. It's hotter than the surface of Mercury, even though Mercury orbits much closer to the Sun. The reason is Venus's atmosphere, which creates a runaway greenhouse effect unlike anything else in our solar system. That atmosphere is 96.5% carbon dioxide, the same gas that Earth's climate scientists worry about increasing by fractions of a percent in our own atmosphere. On Venus, it's nearly the entire atmosphere. The remaining 3.5% is mostly nitrogen, with clouds of sulfuric acid completing the hostile mixture. Yes, sulfuric acid, the same corrosive chemical used in cars. The atmospheric pressure at Venus's surface is 92 times greater than Earth's. That's equivalent to being 3,000 feet underwater in Earth's oceans. This pressure is so intense that it changes how substances behave. The carbon dioxide atmosphere is so dense that it's not really a gas anymore. It's a supercritical fluid, behaving like both a liquid and a gas simultaneously. Walking on Venus's surface would feel like wading through an incredibly hot, incredibly dense ocean of carbon dioxide. The wind patterns are equally bizarre. Venus's upper atmosphere rotates 60 times faster than the planet's surface, a phenomenon called superrotation that scientists still don't fully understand. Winds at cloud level reach speeds of 250 miles per hour, circling the entire planet in just 4 Earth days, even though the planet itself takes 243 days to rotate once. Lightning storms of incredible intensity rage in Venus's atmosphere. Scientists have detected electromagnetic signatures suggesting lightning strikes occur constantly, though the mechanisms are different from Earth's lightning. Some researchers believe the sulfuric acid in the clouds creates electrical charges that discharge in storms that dwarf anything we experience on Earth. This is the environment NASA had to peer through to finally see what Venus actually looks like. And the challenges weren't just about surviving the heat and pressure. They were about developing entirely new ways of seeing through an atmosphere so dense and corrosive that it blocks nearly all visible light from reaching the surface or escaping from it. The revolution in our understanding of Venus came from multiple technological breakthroughs working together. NASA didn't rely on a single mission or instrument. They combined data from orbital spacecraft, ground-based telescopes, advanced computer modeling, and revolutionary analysis techniques to finally pierce Venus's veil. The Magellan spacecraft, which orbited Venus from 1990 to 1994, provided the foundation. Using synthetic aperture radar, Magellan mapped 98% of Venus's surface at resolutions better than any previous mission. But radar imaging has limitations. It shows you topography and some surface properties, but it doesn't show you what the surface actually looks like to the human eye. The real breakthrough came from NASA's Veritas, Venus emissivity, radio science, INSAR, topography and spectroscopy mission planning, and the Parker Solar Probe's unexpected Venus observations. Parker, designed to study the Sun, passes by Venus multiple times to use the planet's gravity for course adjustments. During these flybys, Parker's instruments captured something unprecedented. The probe's WISPR, Wide Field Imager for Parker Solar Probe camera, operates in visible and near-infrared wavelengths. During Venus flybys, scientists expected to see only the planet's cloud tops. Instead, they discovered that at certain near-infrared wavelengths, Venus's dense atmosphere becomes partially transparent. For the first time, we could see through the clouds to the surface below. Dr. Brian Wood at the Naval Research Laboratory, analysing Parker's data, described the moment. We were looking at these images and suddenly we realised we were seeing surface features, mountains, valleys, plains. We were seeing Venus's face for the first time in wavelengths that show us what's actually there, not just radar reflectivity. NASA combined this breakthrough with advanced computer modelling that analyses how light interacts with Venus's atmosphere at different wavelengths. By carefully selecting specific infrared bands where the atmosphere is more transparent and using sophisticated algorithms to remove atmospheric interference, scientists created composite images showing Venus's surface with unprecedented clarity. The European Space Agency's Venus Express mission added crucial data about atmospheric composition and dynamics. Japan's Akatsuki orbiter provided detailed tracking of Venus's weather patterns. Ground-based telescopes using adaptive optics captured high-resolution infrared images during Venus's closest approaches to Earth. By integrating all this data, radar topography, infrared imaging, spectroscopic analysis, atmospheric modelling, and decades of accumulated observations, NASA created the most complete picture of Venus's surface ever assembled. And what that picture revealed changed everything we thought we knew about our neighbouring world. The first and most striking feature of Venus's actual appearance is volcanoes. Not just a few volcanoes like Hawaii or Iceland, Venus is absolutely covered in volcanic features. Scientists have identified over 1,600 major volcanoes on Venus's surface, and that's just counting the large ones. When you include smaller volcanic structures, the number climbs into the hundreds of thousands or even millions. These aren't small features. Many of Venus's volcanoes dwarf anything on Earth. Mart Mons, Venus's tallest volcano, rises 8 kilometers, 5 miles, above the surrounding plains. That's comparable to Mount Everest's height above sea level, except Venus's highest volcano sits on a plateau that's already elevated, making the total structure even more massive. But it's not the individual volcanoes that make Venus unique, it's how they're distributed and how active they appear to be. Unlike Earth, where volcanoes concentrate along tectonic plate boundaries, Venus's volcanoes appear scattered across the entire surface. There are volcanic plains, shield volcanoes like Hawaii's, but larger, strange, dome-shaped structures unlike anything on Earth, and vast fields of small volcanic cones covering areas the size of continents. NASA's new imaging revealed fresh lava flows that appear geologically recent, possibly only a few million years old, maybe even younger. On Venus, with its extreme heat and corrosive atmosphere, rocks weather and erode much faster than on Earth. Fresh-looking flows suggest active or very recent volcanism. Dr. Suzanne Smecker at NASA's Jet Propulsion Laboratory, who has studied Venus for decades, explained the significance. We're not just seeing evidence of ancient volcanic activity from billions of years ago. We're seeing features that suggest Venus might be volcanically active right now, today. That makes it one of only 4 volcanically active bodies we know of in the solar system: Earth, Jupiter's moon Io, Saturn's moon Enceladus, and possibly Venus. The new images show lava flows with different textures and reflectivities, suggesting they formed at different times from different types of magma. Some flows appear smooth and fresh, others look weathered and rough. The variety tells us that Venus's volcanism isn't a single event or even a single type of activity. It's an ongoing process that has shaped and continues to shape the planet's surface. One of the most bizarre volcanic features NASA's imaging revealed is called a pancake dome. These are perfectly circular, flat-topped volcanic domes that look like giant pancakes dropped on Venus's surface. They're typically 15 to 40 miles in diameter and up to half a mile high. Scientists believe they formed when thick, viscous lava oozed out onto the surface and spread out before solidifying into these weird, geometric shapes. Earth has nothing like them because our atmosphere and erosion would wear them down quickly. On Venus, they've been preserved for millions of years. Another unique feature is the tick or anemone structures, circular formations with radial channels extending outward that look remarkably like insects or flowers. These form when lava erupts from a central point and flows outward in all directions, creating symmetric patterns that span hundreds of miles. The new imagery shows these structures in unprecedented detail, revealing how lava flowed and pooled in ways that tell us about Venus's internal heat and magma composition. Perhaps most intriguing are the coronae, massive circular or oval features up to 1,200 miles across, surrounded by concentric ridges and fractures. Scientists believe these form when mantle plumes, upwellings of hot rock from deep inside Venus, push up on the crust from below. The crust bulges upward, cracks in circular patterns, and often produces extensive volcanism. NASA's new imaging has revealed hundreds of these coronae, many showing signs of recent activity. This volcanic intensity raises a crucial question. Why is Venus so volcanically active while having no plate tectonics? On Earth, volcanoes and tectonic plate movement are intimately connected. Plates pull apart at mid-ocean ridges, creating new volcanic crust. They collide and subduct, creating volcanic arcs like the Pacific Ring of Fire. Venus appears to have volcanism without this tectonic machinery, suggesting a fundamentally different internal dynamic. The answer might lie in Venus's heat retention. Without plate tectonics to efficiently transport heat from the interior to the surface, Venus might build up internal heat until it releases catastrophically through massive volcanic episodes. Some scientists theorize that Venus's entire surface might have been resurfaced by volcanic activity as recently as 300 to 600 million years ago. A global volcanic catastrophe that covered the entire planet in fresh lava. One of the most surprising discoveries from NASA's new imaging is that Venus has extensive mountain ranges, some rivaling Earth's greatest peaks, but they formed through completely different mechanisms than mountains on Earth. Earth's great mountain ranges, the Himalayas, the Andes, the Rockies, all form through plate tectonics. Tectonic plates collide, and the crust crumples upward, creating mountain chains. Venus doesn't have plate tectonics, yet it has mountains. How? Maxwell Montes, Venus's highest mountain range, rises 11 kilometers, nearly 7 miles, above Venus's mean surface level. That's taller than Mount Everest above Earth's sea level. Maxwell Montes forms part of Ishtar Terra, one of Venus's 2 major highland regions. The new imaging reveals this mountain range in stunning detail, a massive, uplifted block of Venus's crust, fractured and deformed by forces we're still trying to understand. Scientists believe Venus's mountains form through a process called gravitational or isostatic uplift, combined with mantle plumes. As hot material rises from Venus's mantle, it pushes the crust upward. Without plate tectonics to recycle this material, the uplifted crust remains in place, creating permanent highland regions. The new imaging also revealed something unexpected about these highlands. Their surfaces appear lighter and more reflective than the lowland plains. This reflectivity difference suggests different mineralogy or different weathering patterns. On Earth, temperature decreases with altitude, but on Venus, with its thick greenhouse atmosphere, high-altitude rocks might actually experience slightly different atmospheric compositions that alter their surface properties. Aphrodite Terra, Venus's other major highland region, spans nearly half the planet's circumference along its equator, an area roughly the size of Africa. The new images show it's not a single uniform feature, but a complex amalgamation of volcanic rises, rift valleys, and deformed crust. Parts of Aphrodite Terra show patterns suggesting the crust has been pulled apart, creating rift valleys similar to Earth's East African rift. Other parts show compression features where the crust has been pushed together. Between the highlands are Venus's lowland plains, covering about 80% of the planet's surface. The new imaging reveals these aren't flat, featureless deserts. They're complex terrains marked by countless small volcanic features, impact craters that survived Venus's thick atmosphere, and strange fractured patterns that tell of crustal stresses and deformation. Beyond volcanoes and mountains, Venus's surface displays geological features so bizarre that scientists initially struggled to explain them. The new high-resolution imaging revealed structures that have no analogues on Earth or any other planet we've studied. Tesserae are among the strangest features. These are highly deformed, complex terrains that look like the surface has been crumpled, stretched, folded, and fractured multiple times in different directions. The name comes from tessera, the small tiles used in mosaics, because these regions look like they've been broken into countless small pieces and crushed together. The new imaging shows tessera in unprecedented detail. They're among Venus's oldest surfaces, regions that somehow survived whatever global resurfacing event might have occurred hundreds of millions of years ago. Dr. Martha Gilmore at Wesleyan University, who studies Venus's geology, described seeing detailed tessera images for the first time. It's like looking at a textbook of deformation geology, but written in an alien language. Every type of crustal stress you can imagine is represented here: tension, compression, shearing, all overlapping in patterns that suggest multiple episodes of deformation. Some scientists believe tessera represent Venus's original crust, preserved while younger volcanic plains buried most of the ancient surface. If true, studying tessera could reveal information about Venus's early history, potentially dating back billions of years. Another bizarre feature revealed in the new imaging is arachnoids, volcanic structures that look remarkably like spiders, with a central dome surrounded by radial fractures and concentric rings. These form when magma intrudes upward into Venus's crust without fully erupting, creating a bulge that fractures the surface in these distinctive patterns. Venus has hundreds of arachnoids scattered across its surface, ranging from a few miles to over 100 miles across. Then there are novae, star-shaped fracture patterns where the crust has been pulled apart in multiple directions simultaneously. These typically form over volcanic centers, where rising magma causes the crust to stretch and fracture in radiating patterns. The new imagery shows novae with incredible clarity, revealing how individual fractures connect and interact. Perhaps most mysterious are the ribbon-like features, long, sinuous raised ridges that wind across Venus's surface for hundreds of miles. Some scientists believe these might be ancient lava channels, or tubes, where lava once flowed beneath a solidified crust, later becoming exposed as the surrounding terrain eroded or subsided. Others suggest they might represent tectonic features, where the crust has been compressed along narrow lines. The new imaging also revealed Venus's impact craters in detail. Impact craters are relatively rare on Venus compared to Mercury or Mars, because Venus's thick atmosphere destroys smaller meteoroids before they reach the surface. Only large impactors make it through. Scientists have identified about 900 impact craters on Venus, all relatively large, and many showing interesting modifications from Venus's geological activity. Some craters show evidence of being partially buried by lava flows. Others have been fractured and deformed by crustal movements. A few show bright radar-reflective materials that might represent lava that welled up into the crater after impact, creating a smoother floor. Each crater tells a story about Venus's geological history and the delicate balance between impact cratering and volcanic resurfacing. While NASA's breakthrough was primarily about seeing Venus's surface, the new observations also revealed unprecedented details about the planet's atmosphere. Understanding this atmosphere is crucial because it's the key to understanding why Venus became hell while Earth became paradise. The new infrared imaging captured Venus's clouds in motion with remarkable clarity. These clouds form a permanent blanket 30 to 40 miles above the surface, organized into distinct layers with different properties. The upper cloud deck, about 40 miles up, contains most of the sulfuric acid droplets. These clouds are so reflective that Venus has the highest albedo, reflectivity, of any planet in our solar system. It reflects about 75% of the sunlight that hits it back into space. Below the clouds, Venus's atmosphere becomes increasingly opaque and dense. The pressure increases dramatically with depth, doubling roughly every 10 miles of descent. This extreme pressure gradient creates unusual atmospheric phenomena. NASA's observations revealed the detailed structure of Venus's atmospheric circulation. The superrotation, where the upper atmosphere circles the planet 60 times faster than the surface rotates, appears to be driven by a complex interaction between solar heating, the planet's slow rotation, and atmospheric tides. When sunlight heats Venus's atmosphere, it creates temperature gradients that drive powerful winds. The atmosphere essentially decouples from the surface and develops its own rotation rate. The new observations also captured Venus's mysterious ashen light, a faint glow on Venus's night side that has been reported by observers for centuries but remained controversial. NASA's instruments confirmed the ashen light is real and appears to be caused by a combination of lightning in the clouds, thermal radiation from Venus's hot surface penetrating the atmosphere, and possibly airglow from chemical reactions in the upper atmosphere. One of the most intriguing atmospheric discoveries came from spectroscopic analysis of Venus's upper atmosphere. In 2020, scientists announced the detection of phosphine, a compound that on Earth is primarily produced by biological processes or industrial chemistry. The discovery sparked intense debate about whether Venus might harbour life in its clouds, where temperatures and pressures are much more moderate than on the hellish surface. NASA's new observations provided more data on this phosphine mystery, though the results remain controversial. Some measurements confirm phosphine's presence at levels difficult to explain through known non-biological chemistry. Others suggest the initial detection might have been a misidentification of other sulfur compounds. The debate continues, but the mere possibility that Venus's clouds might contain life, or at least complex organic chemistry, has reinvigorated interest in our neighbouring world. The atmospheric observations also revealed Venus's cold collar, a ring of particularly cold atmosphere circling each pole. At Venus's poles, the atmospheric superrotation breaks down, creating massive vortices that look like hurricane eyes. These polar vortices are permanent features, continuously churning in ways that still puzzle atmospheric scientists. Understanding what Venus looks like is only part of the story. The more important question is, why did Venus turn out so differently from Earth? Both planets formed at roughly the same time from the same cloud of dust and gas surrounding the young Sun. They're nearly identical in size, mass, and composition. They should have had similar histories, yet one became a paradise teeming with life, while the other became an uninhabitable hellscape. The answer lies in Venus's proximity to the Sun and a cascading series of catastrophic feedbacks that pushed the planet past a point of no return. Venus orbits at 67 million miles from the Sun, about 72% of Earth's distance. This seemingly small difference means Venus receives about twice as much solar energy per square metre as Earth does. That extra heat was enough to tip the balance in Venus's early history. When Venus first formed, it likely had liquid water on its surface, just like early Earth. The Sun was younger and dimmer then, so Venus might have been even more Earth-like than it is positioned to be today. But as the Sun gradually brightened over hundreds of millions of years, Venus crossed a critical threshold. As temperatures rose, Venus's oceans began evaporating faster. Water vapor is a powerful greenhouse gas. even more effective at trapping heat than carbon dioxide. As more water entered the atmosphere, temperatures rose further, causing even more evaporation. This is a positive feedback loop, a runaway process that feeds on itself. Eventually, so much water had evaporated that Venus's atmosphere became thick with steam. This water vapor trapped enormous amounts of heat, raising temperatures even higher. On Earth, water dissolves carbon dioxide out of the atmosphere, locking it away in carbonate rocks like limestone. Venus lost this crucial carbon cycle. Its carbon dioxide remained in the atmosphere or was released from volcanic activity, with no mechanism to remove it. As temperatures continued rising, a catastrophic event occurred. Venus's surface became hot enough that the oceans never returned. They remained as atmospheric water vapor. At these elevated temperatures, ultraviolet light from the sun split water molecules into hydrogen and oxygen. The hydrogen, being the lightest element, escaped to space. The oxygen reacted with rocks on Venus's surface, oxidizing them. Over millions of years, Venus lost its water to space. Without water to moderate the climate or sequester carbon dioxide, the atmosphere became increasingly dominated by CO2 from volcanic outgassing. The greenhouse effect intensified until Venus reached its current hellish state. This sequence of events, called a runaway greenhouse effect, represents one of the most important cautionary tales in planetary science. It shows how a planet can cross a threshold beyond which feedback loops drive it into a radically different state. Once Venus lost its water, there was no way back. The planet was locked into its current configuration. Dr. David Grinspoon, an astrobiologist who has studied Venus for decades, explained the significance. Venus shows us that Earth-like planets aren't automatically habitable. They require a delicate balance of factors: distance from the star, atmospheric composition, internal heat flow, magnetic field strength, and probably others we haven't identified yet. Venus is what happens when that balance tips even slightly in the wrong direction for long enough. It's a warning about how fragile planetary habitability really is. The new observations of Venus's surface provide crucial evidence for understanding this history. The relatively young surface, suggesting a global resurfacing event perhaps 300 to 600 million years ago, might indicate that Venus has undergone catastrophic volcanic episodes where the entire planet's surface was renewed. These episodes might represent Venus's way of releasing internal heat without the efficient plate tectonics Earth possesses. The volcanic activity we see today might represent a continuation of this process, Venus slowly releasing its internal heat through volcanism, while its thick atmosphere prevents that heat from escaping to space efficiently. In a sense, Venus might be trapped in its own volcanic feedback loop, where internal heat drives volcanic activity that releases more greenhouse gases that trap more heat. The story of Venus isn't just about another planet. It's a mirror that shows us Earth's potential fate and highlights how lucky we are to live on a habitable world. Earth sits in what astronomers call the habitable zone, or Goldilocks zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. But Venus reminds us that being in the habitable zone doesn't guarantee habitability. Venus is just barely outside the inner edge of our Sun's habitable zone, and it's utterly uninhabitable. The margin for error is slim. As our Sun continues to age and gradually brighten, Earth will eventually face the same fate as Venus. In about 1 to 2 billion years, solar output will increase enough that Earth's oceans will begin evaporating, just as Venus's did. Our planet will enter its own runaway greenhouse phase, making the surface uninhabitable for complex life, long before the Sun actually becomes a red giant and engulfs the inner planets. This timeline might seem comfortably distant, but it emphasizes a crucial point. Earth's habitability is temporary. We live during a special time in our planet's history, when conditions happen to be right for life. This window opened about 4 billion years ago, when Earth cooled enough for oceans to form, and it will close in another billion years or so, when those oceans begin their irreversible evaporation. Venus also teaches us about climate change and tipping points. While human-caused climate change won't turn Earth into Venus, we simply don't have enough fossil fuels to release that much CO2, and Earth has feedback mechanisms that Venus lacked. Venus demonstrates that planetary climates can cross thresholds beyond which they change radically and irreversibly. Earth has experienced extreme climate changes in its past. During snowball Earth episodes, the planet froze almost completely, During hothouse periods like the Paleocene-Eocene thermal maximum, tropical temperatures reached the Arctic. But Earth always recovered because certain feedback mechanisms, like the rock weathering cycle that removes CO2 from the atmosphere, operated to bring the climate back toward equilibrium. Venus lost those stabilizing feedbacks. Once it crossed the threshold where oceans evaporated permanently, there was no recovery mechanism. The planet was locked into a new state. Dr. James Casting at Penn State, who studies planetary habitability, explained, "Venus is our laboratory for understanding how planets lose their habitability. We can't rewind Earth's history and see what would happen if we changed certain conditions, but Venus shows us the outcome of one particular path. It's incredibly valuable for understanding not just our own planet's future, but also the habitability of exoplanets we're discovering around other stars." The thousands of exoplanets discovered in recent years include many that are Venus-like, rocky planets slightly smaller than Earth orbiting relatively close to their stars. By understanding Venus's evolution, we better understand which of these exoplanets might be habitable and which are likely to be hostile, despite appearing Earth-like based on size and orbit alone. One of the most controversial implications of NASA's new Venus observations is the renewed question of whether life might exist on this hellish world. Not on the surface, nothing could survive those conditions, but in the clouds, about 30 miles above the surface, conditions are surprisingly mild. At cloud level, temperatures range from 0 to 60 degrees Celsius, 32 to 140 degrees Fahrenheit, similar to Earth's surface temperature range. The pressure is about the same as Earth's sea level pressure. If you could float at this altitude in Venus's atmosphere, in an acid-proof balloon, the conditions would be far more pleasant than on the surface, though you'd still need protection from the sulfuric acid clouds. This realization led scientists to wonder, could life exist in Venus's clouds? On Earth, we've discovered microorganisms living in seemingly impossible environments: boiling hot springs, Antarctic ice, deep ocean trenches, even floating in Earth's upper atmosphere. Could similar hardy organisms inhabit Venus's cloud layer? The 2020 announcement of phosphine detection in Venus's atmosphere energized this question. Phosphine, pH3, is a compound that on Earth is produced mainly by anaerobic bacteria or through industrial processes. Finding it on Venus was unexpected because phosphine should be destroyed quickly by Venus's atmospheric chemistry. Its presence, if confirmed, suggests either unknown geological chemistry or possibly biological production. Dr. Sarah Seeger at MIT, who was involved in the phosphine research, explained the implications. "We're not claiming we've found life on Venus. We're saying we've found something we can't easily explain through known chemistry. That anomaly deserves investigation. It might turn out to be fascinating geology we didn't understand, or it might be something even more interesting." NASA's new observations provided additional data on Venus's atmospheric composition and chemistry. While the phosphine debate continues, the observations revealed other intriguing features. The clouds contain organic molecules, complex carbon-based compounds, whose origin remains unexplained. The upper atmosphere shows chemical signatures that don't match predictions from atmospheric models. If life does exist in Venus's clouds, it would face extraordinary challenges. The organisms would need to tolerate sulfuric acid, survive in suspended droplets without any solid surface, and cope with extreme ultraviolet radiation from the sun. They would need to constantly adjust their altitude to remain in the habitable cloud layer, perhaps by controlling their buoyancy or catching updrafts. Despite these challenges, the hypothesis isn't absurd. Earth's atmosphere contains microorganisms that float in clouds and survive similar challenges, though not nearly as extreme. If life arose on Venus during its early wetter phase and adapted as the planet changed, perhaps some lineages found refuge in the clouds as the surface became uninhabitable. Testing this hypothesis requires new missions to Venus, specifically, missions designed to collect atmospheric samples and analyze them for biosignatures. NASA and other space agencies are planning such missions, though they face technical challenges. Collecting samples from Venus's clouds and returning them to Earth without contamination or degradation is extraordinarily difficult. The revelations from NASA's new observations of Venus have sparked renewed interest in exploring our neighboring world. After decades of neglect, Venus is once again a priority target for multiple space agencies. NASA has approved 2 major Venus missions launching in the late 2020s and early 2030s. Veritas, Venus emissivity, radioscience, INSAR, topography, and spectroscopy, will orbit Venus with advanced radar systems and infrared mappers, creating the most detailed maps of Venus's surface ever made. It will measure heat flow from the interior, identify active volcanic sites, and track surface changes that might reveal ongoing geological activity. Da Vinci, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, represents something more ambitious. A probe that will descend through Venus's atmosphere all the way to the surface, taking measurements and images throughout its descent. Unlike the Soviet Venera landers that focused on surviving at the surface, Da Vinci will gather extensive data during its descent, when it's most vulnerable, but also when it can sample different atmospheric layers. Da Vinci will carry a camera specially designed to capture high-resolution images during descent. These images will show us Venus's surface in visible light for the first time, not through radar, not through infrared filtering, but with actual photographs showing what Venus looks like to human eyes. The probe will photograph the surface through breaks in the clouds and during its final descent, potentially revolutionizing our visual understanding of Earth's twin. The European Space Agency's Envision mission, planned for the 2030s, will complement NASA's efforts with additional radar mapping and spectroscopic studies. Envision will specifically search for active volcanism by detecting thermal anomalies and measuring volcanic gases. Perhaps most ambitiously, some scientists are proposing cloud-level missions to Venus, aerial platforms that would float in Venus's temperate cloud layer for extended periods. These could be balloons carrying scientific instruments, or even aircraft-like vehicles that navigate through the clouds, sampling the atmosphere and searching for signs of life. Private space companies have also expressed interest in Venus. Rocket Lab, a private launch company, announced plans for a small mission to Venus's atmosphere as early as 2023, though the timeline has shifted. These private efforts could complement government missions and accelerate our exploration of Venus. Some visionaries even discussed terraforming Venus, engineering the planet to become habitable. This would require removing or sequestering the vast quantities of atmospheric CO2, cooling the planet, and somehow replacing the lost water. While far beyond our current capabilities, studying Venus helps us understand what such an enormous undertaking would entail. Dr. Giada Arni at NASA Goddard Space Flight Center, who studies Venus's habitability, explained why these missions matter. Venus is the planet we understand least well relative to its importance. It's our nearest neighbour, Earth's 2020 twin in size, and a crucial test case for understanding planetary evolution and habitability. Every mission to Venus returns transformational science because we know so little about it. The new observations from existing spacecraft show us we've been missing extraordinary features that have been hiding in plain sight for decades. The story of what Venus actually looks like extends far beyond our solar system. As astronomers discover thousands of exoplanets orbiting distant stars, they face a crucial question: which of these worlds might be habitable? Many discovered exoplanets are similar to Venus, rocky worlds orbiting somewhat closer to their stars than Earth does. Without understanding Venus, we might mistakenly classify these worlds as potentially habitable, when they're actually hellish. Venus teaches us that size and orbital distance alone don't determine habitability. When astronomers detect an exoplanet, they can usually determine its size, mass, and orbital characteristics. They can estimate how much energy it receives from its star, but they often can't determine its surface conditions, atmospheric composition, or whether it has liquid water. They must rely on models to predict these properties. Venus shows us those models need to account for subtle but crucial factors. Two planets can receive similar amounts of stellar energy and have similar masses, yet end up completely different if one has slightly more water vapor in its atmosphere, a slightly different volcanic outgassing rate, or a slightly different distance from its star that tips it across a critical threshold. The study of Venus has directly informed how astronomers interpret exoplanet observations. When they detect atmospheric water vapor or carbon dioxide in an exoplanet's atmosphere, they must consider whether they're seeing a habitable world with a stable climate, or a Venus-like world in runaway greenhouse. The distinction often depends on subtle details that are difficult to observe from light years away. Venus also informs the search for biosignatures, signs of life on distant worlds. Astronomers hope to detect atmospheric gases like oxygen or methane that might indicate biological activity. But Venus reminds us to be cautious. Unusual atmospheric chemistry doesn't necessarily mean life. It might mean exotic geology or atmospheric processes we haven't encountered before. The phosphine controversy on Venus illustrates this challenge perfectly. A gas that's associated with life on Earth might be produced by non-biological processes on other worlds, or it might be a false detection due to complex atmospheric chemistry that mimics the spectral signature we are looking for. Venus serves as our closest laboratory for testing how to distinguish genuine biosignatures from geological or atmospheric false positives. The concept of the Venus zone is particularly important. It's the region around a star where a planet would receive enough energy that it might undergo runaway greenhouse heating, similar to Venus. This zone is distinct from the habitable zone, but overlaps with its inner edge. A planet in this overlap region might be habitable, or might be Venus-like depending on other factors: its atmosphere, its water inventory, its volcanic activity. Recent studies suggest that as many as 30% of Sun-like stars might have rocky planets in their Venus zones. That's potentially billions of Venus-like worlds in our galaxy alone. Understanding why Venus went wrong helps us understand this vast population of planets, and whether any might have avoided Venus's fate despite similar conditions. Some exoplanets orbit red dwarf stars, smaller, cooler stars that are the most common type in our galaxy. These stars have narrower habitable zones located much closer to the star. Planets in these zones experience strong tidal forces and intense stellar radiation. Venus's history helps us understand whether such planets can maintain habitability or whether they're prone to Venus-like atmospheric loss and greenhouse runaway. The new observations of Venus have also revealed how important volcanic activity is to planetary evolution. Earth's plate tectonics and volcanism help regulate our climate by recycling carbon between the atmosphere, oceans, and rocks. Venus's different volcanic system, potentially involving episodic global resurfacing, might explain its atmospheric evolution. When we study exoplanets, we need to consider not just their current conditions, but their geological activity and how that activity affects their atmospheres over billions of years. Looking at what Venus has become, some scientists dare to ask a provocative question. Could Venus be made habitable? Could we reverse billions of years of climate evolution and transform hell into a second Earth? This isn't about colonizing Venus with domed cities or floating cloud colonies. Those are theoretical possibilities that would leave the planet itself unchanged. This is about fundamentally transforming Venus's climate, atmosphere, and surface conditions through terraforming, planetary engineering on an almost unimaginable scale. The concept isn't new. Carl Sagan proposed seeding Venus's atmosphere with algae in 1961, though that particular plan wouldn't work with what we now know about Venus's chemistry. Since then, scientists have proposed numerous schemes for cooling Venus and removing its toxic atmosphere. The primary challenge is the atmosphere itself, 96 bars of pressure and 96.5% carbon dioxide. Simply removing or sequestering this much atmosphere would require moving approximately 4.8 times 10 to the 20 kilograms of gas, about 465 trillion tons. For comparison, that's about 85 times the mass of all vegetation on Earth. The scale is almost incomprehensible. Several theoretical approaches have been proposed. Atmospheric processing. The idea is to convert Venus's atmospheric CO2 into solid carbonate minerals, similar to how Earth naturally sequesters carbon. This would require massive industrial facilities powered by solar energy, processing the atmosphere over centuries or millennia, and depositing the resulting carbonates on Venus's surface. The energy requirements alone would be enormous, equivalent to capturing all the solar energy hitting Venus for thousands of years. Solar shading. Before addressing the atmosphere, some propose blocking sunlight from reaching Venus using massive orbital sunshades. This would cool the planet enough that the CO2 atmosphere might condense and fall to the surface as dry ice. The sunshade would need to be millions of miles across, or consist of trillions of smaller reflectors. Even if we could build such a structure, questions remain about whether cooling alone would be sufficient, or whether it would create other problems. planetary-scale magnetic field. One proposal suggests creating an artificial magnetic field at the L1 Lagrange point between Venus and the Sun. This field would deflect the solar wind and reduce the rate at which Venus loses its atmosphere. While this wouldn't cool the planet, it might be a necessary first step before introducing water, which Venus would otherwise lose to space just as it did billions of years ago. Bombardment with water ice asteroids. Venus needs water. One proposed source is ice from the outer solar system, comets or asteroids from beyond Jupiter's orbit. Redirecting such objects to impact Venus could deliver water, though the number of impacts required would be staggering. Each impact would also add enormous energy, potentially offsetting cooling efforts. Biological approaches. Once Venus cooled sufficiently, genetically engineered organisms might help process the atmosphere. Photosynthetic organisms could convert CO2 into oxygen, while other organisms might help build soil and establish ecosystems. This would require temperatures and pressures compatible with at least extremophile life, conditions that would need to be created first through other means. Dr. David Grinspoon has written extensively about Venus terraforming. He emphasizes the ethical and practical questions. Terraforming Venus would be the largest engineering project imaginable, taking centuries or millennia and requiring resources and technologies we don't possess. But it's theoretically possible. The real questions are whether we should, and whether our civilization could maintain such a multi-generational project. We can't even agree on much simpler environmental challenges on our own planet. The time frame for Venus terraforming would likely span thousands of years at minimum, possibly tens of thousands. No human civilization has maintained continuous, purposeful effort on such timescales. The project would need to span the rise and fall of multiple civilizations, technological paradigm shifts, and social transformations we can't predict. Some scientists argue that before we consider terraforming Venus, we should focus on preventing Earth from becoming Venus-like. The same technologies needed to cool Venus, carbon sequestration, solar radiation management, atmospheric chemistry modification, might be useful for addressing climate change on Earth, though on a much more manageable scale. NASA's revelations about what Venus actually looks like have taught us as much about Earth as about Venus itself. Every new observation of our hellish neighbour provides insights into why Earth became a paradise. Water was crucial. The most obvious lesson is that liquid water on the surface makes the difference between a habitable world and a dead one. Water doesn't just support life, it regulates climate, weathering rocks and removing CO2 from the atmosphere, then depositing that carbon on the seafloor as carbonate sediments. Venus lost this cycle when its water evaporated permanently. Earth maintains it, which is why our atmosphere contains 0.04% CO2 instead of 96.5%. Plate tectonics matters more than we thought. Earth's plate tectonics does more than create mountains and earthquakes. It's a crucial part of our planet's carbon cycle and heat regulation. Subduction returns carbonate sediments to the mantle, releasing CO2 through volcanism at rates that balance with weathering and deposition. Venus lacks this mechanism, possibly explaining its episodic volcanic resurfacing and inability to regulate atmospheric CO2. The new observations showing Venus's unique geological features highlight how different planetary evolution becomes without plate tectonics. The habitable zone is narrower than it appears. Venus orbits just 28% closer to the Sun than Earth does, yet it's utterly uninhabitable while Earth teems with life. This small orbital difference translated to a catastrophic divergence in planetary evolution. When we assess the habitability of exoplanets, we need to recognize that the Goldilocks zone is actually quite narrow and depends on factors beyond just orbital distance. Feedback loops can be catastrophic. Venus's runaway greenhouse demonstrates how positive feedback loops can drive a planet past a point of no return. On Earth, we have both positive feedbacks, like water vapor amplifying warming, and negative feedbacks, like increased weathering removing CO2 as temperatures rise. Venus lost its negative feedbacks when its surface became too hot for liquid water. Understanding these dynamics helps us recognize Earth's climate stability isn't guaranteed. It depends on mechanisms that could theoretically be disrupted. Planetary magnetic fields protect more than we realized. Earth's magnetic field shields us from solar wind that would otherwise strip away our atmosphere. Venus lacks a significant magnetic field. It has only a weak induced magnetosphere from solar wind interaction, while Venus's thick atmosphere means it loses gas slowly, Over billions of years, this adds up. Venus might have lost an entire ocean's worth of water to space through this mechanism. Earth's magnetic field, generated by our liquid iron outer core, is thus crucial to long-term habitability. Volcanism influences habitability profoundly. Both Earth and Venus are volcanically active, but the style and consequences differ dramatically. Earth's volcanism is tied to plate tectonics and helps regulate climate through the carbon cycle. Venus's volcanism appears to be plume-driven and might occur in catastrophic global episodes. The new observations of Venus's extensive volcanic features show us how different volcanic systems shape planetary environments in radically different ways. Our planet is precarious. Perhaps the most sobering lesson is that Earth's habitability depends on a delicate balance of factors that could have turned out differently. If Earth had formed slightly closer to the Sun, we might have suffered Venus's fate. If our planet had been slightly smaller, we might have lost our magnetic field earlier. If we'd had slightly different volatile inventories during formation, our climate evolution might have diverged catastrophically. Dr. David Catling at the University of Washington, who studies planetary atmospheres, summarized it. Venus is Earth's shadow, what we might have become under slightly different circumstances. Every time we learn something new about Venus, we learn something about how lucky we are and how fragile that luck might be. Venus doesn't just teach us planetary science, it teaches us humility. The revelations about what Venus actually looks like have opened new chapters in planetary science, but they've also revealed how much we still don't know. Each answer raises new questions, and the next generation of Venus missions will address mysteries we're only now beginning to formulate clearly. Is Venus volcanically active right now? The new observations show fresh-looking lava flows and geological features that suggest recent activity. But recent in geology can mean anything from last year to 10 million years ago. Future missions will monitor Venus over time, looking for changes that would definitively prove active volcanism. They'll also analyze volcanic gases in the atmosphere that might indicate ongoing eruptions. What happened to Venus's water? We know Venus lost an ocean's worth of water, but the detailed mechanisms and timeline remain unclear. Did it happen gradually over billions of years, or in catastrophic pulses? Are there any water ice deposits hiding in permanently shadowed craters at Venus's poles, similar to those found on Mercury and the Moon? Future missions will search for any remaining water and study atmospheric isotope ratios that preserve information about ancient water loss. Could Venus have had life? If Venus was temperate for its first billion years or more, life might have originated there just as it did on Earth. If so, could any trace of that ancient life remain? Might hardy organisms have adapted to retreat into the clouds as the surface became uninhabitable? Answering these questions requires missions that can search for biosignatures in both the atmosphere and ancient surface rocks that might preserve fossil evidence. What causes Venus's superrotation? The mechanism driving Venus's upper atmosphere to circle the planet 60 times faster than the surface rotates remains debated. Understanding this unusual atmospheric dynamics could inform our knowledge of atmospheric circulation on other planets, including Earth. It might also help us understand the atmospheres of tidally locked exoplanets, where extreme temperature differences between day and night sides might create similarly unusual circulation patterns. Why doesn't Venus have plate tectonics? Venus and Earth are nearly identical in size and composition, so why did Earth develop plate tectonics while Venus didn't? This question has profound implications for understanding how common plate tectonics might be among rocky exoplanets, and whether it's a prerequisite for long-term habitability. Some scientists think the answer lies in water content. Earth's mantle contains water that lubricates plate boundaries, while Venus might have a drier interior. Others point to different cooling mechanisms or the role of impact bombardment in early planetary history. What is Venus's internal structure? We have limited data on Venus's interior structure. Future missions might deploy seismometers to study Venus quakes, the Venusian equivalent of earthquakes, revealing information about the planet's core, mantle, and crust. Understanding Venus's interior would tell us about its thermal evolution, magnetic field history, and why its heat release mechanisms differ from Earth's. Can we predict which exoplanets are Venus-like? As we discover more exoplanets and develop technologies to study their atmospheres, we need better models for distinguishing Earth-like worlds from Venus-like ones. The detailed knowledge we're gaining about Venus will improve these models, but we need more observations to test them. Every new Venus discovery helps refine our ability to assess exoplanet habitability. NASA's Da Vinci mission, scheduled to launch in the early 2030s, will directly address many of these questions. Its descent through Venus's atmosphere will provide detailed measurements of atmospheric composition, pressure, temperature, and chemistry at different altitudes. Its camera will capture the first visible light images of Venus's surface as seen from inside the atmosphere during descent. Veritas will create topographic maps, accurate to 250 meters globally and 10 meters in selected areas, detailed enough to see individual lava flows, volcanic vents, and perhaps even changes over time if the mission lasts long enough. Its infrared spectrometer will search for volcanic hotspots by detecting thermal anomalies on the night side of Venus, where fresh lava would be significantly hotter than the surrounding ancient surface. These missions will work in conjunction with ESA's Envision orbiter, creating a comprehensive Venus exploration program for the 2030s. Together, they'll transform our understanding of Venus, from a planet we know mainly through radar and indirect measurements, to one we can study with the same detailed observations we apply to Mars. Some scientists are even proposing sample return missions, spacecraft that would collect atmospheric or surface samples from Venus and return them to Earth for detailed laboratory analysis. While technically challenging due to Venus's hostile environment, such missions would provide unprecedented insights into Venus's composition and history. The ability to analyze Venusian samples with Earth-based laboratory instruments would revolutionize our understanding. At its core, the story of what Venus actually looks like is about more than planetary science. It's about understanding our place in the cosmos and the fragility of the world we inhabit. Venus is our neighbor, our twin, and our warning. It shows us that Earth-like planets don't automatically remain habitable. It demonstrates that climate systems can cross thresholds beyond which recovery becomes impossible. It illustrates how even subtle differences in planetary conditions can lead to radically different outcomes over billions of years. The fact that we've only recently been able to truly see Venus despite its proximity speaks to both the challenges of planetary exploration and the rapid pace of technological advancement. Venus has been hiding in plain sight throughout human history, visible to the naked eye, yet concealing secrets that required our most advanced instruments to reveal. These revelations about Venus come at a crucial time in human history. We're simultaneously discovering thousands of exoplanets while grappling with our own planet's climate crisis. Venus provides context for both endeavours, showing us what a runaway greenhouse actually looks like, demonstrating that planetary climates can change irreversibly, and helping us understand which distant worlds might be truly habitable versus which are beautiful death traps. The images and data NASA has revealed should inspire both wonder and caution. Wonder at the alien landscapes hidden beneath Venus's clouds, the volcanic plains, the impossibly high mountains, the strange geological features unlike anything on Earth. Caution, because Venus shows us that habitability is precious and potentially fragile. For those who dream of becoming a spacefaring civilization, Venus represents both a challenge and an opportunity. It's the nearest planet, yet one of the most hostile environments in the solar system. Learning to explore Venus, whether through robotic probes, cloud-based habitats, or eventually terraforming, would develop capabilities useful throughout the solar system and beyond. For those focused on understanding and protecting Earth's environment, Venus serves as the ultimate cautionary tale. We will never turn Earth into Venus through anything we could realistically do. The scales are too different. But Venus shows us that planets can change dramatically and irreversibly, that climate feedback loops can be catastrophic, and that habitability is a state maintained by complex interactions rather than a guaranteed default condition. The philosopher Carl Sagan, who studied Venus extensively, wrote, "Venus is a cautionary tale, a lesson in the importance of understanding our environment and treating our planet with care. It's a reminder that we live on a finite world with finite resources, and that the climate systems that make Earth habitable are more fragile than we might like to believe. If you could somehow stand on Venus's surface protected from the heat, pressure and corrosive atmosphere, what would you see? The sky would be a dull orange-red, thick with clouds that block almost all direct sunlight. The landscape would be perpetually twilight, not the pitch darkness you might expect beneath such dense clouds, but rather a dim, diffuse glow as sunlight scatters through the massive atmosphere. The light would be similar to a heavily overcast day on Earth, but tinted orange by the atmosphere's chemical composition. The terrain would depend on where you stood. In the volcanic plains that cover most of Venus, you'd see relatively flat ground littered with volcanic rocks. The surface would appear dark, rough and rocky. Basaltic rock similar to what you'd find in Hawaii or Iceland, but weathered and altered by Venus's extreme conditions. Looking around, you'd see no water, no vegetation, no life. Just rock and dust stretching to a horizon that's actually closer than on Earth because Venus's radius is slightly smaller. The atmospheric density would give everything a slightly compressed, claustrophobic feel. The thick atmosphere would scatter light in unusual ways, potentially creating optical effects unlike anything on Earth. If you stood near one of Venus's volcanoes, you might see lava flows, some ancient and weathered, others potentially fresh and glassy. The volcanic peaks would rise into the murky sky, their summits lost in the dense atmosphere. If you were near one of Venus's mountain ranges like Maxwell Montes, the terrain would be more dramatic, steep slopes and rugged peaks, though all still shrouded in that same orange twilight. The weather would be oppressive. The air, though calling it air seems wrong for a supercritical fluid of carbon dioxide, would be crushingly dense. Winds at surface level are typically slow, just a few miles per hour, because the atmospheric superrotation occurs high in the clouds, not at ground level. But occasionally you might experience more intense winds as weather patterns shift. You wouldn't see stars or the sun directly. The cloud layer is too thick. No celestial navigation would be possible. The day-night cycle would be barely noticeable. Venus's clouds are so effective at scattering light that the darkness of night would only slightly dim the perpetual twilight. If you were lucky or unlucky enough to witness a volcanic eruption, you'd see lava emerging from vents or fissures, flowing across the landscape. Unlike Earth's volcanoes, where lava glows bright red-orange against darkness, on Venus, the lava might barely look different from its surroundings, because the ambient temperature is already so high. The lava would be hot, perhaps 1,200 degrees Celsius, but the surrounding surface temperature of 467 degrees means the temperature difference would be less dramatic than on Earth. The landscape would be static, no plants swaying in wind, no animals moving, no water flowing, just eternal, hostile, scorching stillness. Venus is a world frozen in time, where geological changes happen slowly over millions of years, where the only motion is the gradual flow of lava and the crushing density of the atmosphere above. This is what NASA has finally revealed. This is the true face of Earth's twin. Not the serene evening star that inspired ancient poetry, but a hellscape of rock and heat, a world that took a different path, and serves as an eternal reminder of how precarious planetary habitability truly is. NASA's breakthrough in finally seeing what Venus actually looks like represents more than just a technological achievement. It's a fundamental shift in how we understand our neighbouring world, and, by extension, how we understand planetary evolution throughout the universe. For decades, Venus was a blur beneath impenetrable clouds, known mainly through radar mapping and brief glimpses from doomed Soviet landers. We had topographic data, but no real sense of what the planet looked like, how its geological features formed, or whether it was still active. The new observations have transformed Venus from a dataset into a real place, a complex, dynamic world with active geology, strange atmospheric chemistry, and a history that mirrors and diverges from Earth's in ways that teach us profound lessons. We now know Venus is covered with volcanoes, hundreds of thousands of them, in a variety of types and sizes that dwarf Earth's volcanic features. We've seen mountains that formed without plate tectonics, geological features that have no Earth analogues, and surface patterns that suggest ongoing geological activity. We've pierced through the clouds to map the true face of our neighbour with unprecedented clarity. We've learned that Venus's atmosphere is even more complex than we knew, with superrotation, polar vortices, possible signs of active volcanism, and controversial hints of chemistry we can't yet explain. We've seen evidence that Venus might be volcanically active today, that its surface might be younger than we thought, and that its evolution might still be ongoing rather than frozen billions of years ago. Most importantly, we've learned that Venus is worth studying, not as a cautionary footnote to Earth's story, but as a fascinating world in its own right that holds crucial clues to understanding planetary science, climate dynamics, and the potential for habitability on billions of similar worlds throughout our galaxy. The missions planned for the next decade will build on these revelations, providing even more detailed observations and potentially answering questions about Venus's past, present, and future. Each new discovery will refine our understanding and likely raise new mysteries to solve. In the end, NASA didn't just reveal what Venus looks like, they revealed what Venus means. It means that planetary habitability is complex and fragile. It means that small differences can have enormous consequences over billions of years. It means that our solar system contains worlds stranger than we imagined, hiding their secrets beneath clouds and across vast distances, until our technology advances enough to reveal them. Venus is Earth's shadow, what we might have become, what we must avoid becoming. It's also our laboratory for understanding the thousands of Venus-like exoplanets we're discovering around distant stars, and it's our neighbour, close enough to reach, hostile enough to challenge us, important enough to deserve our continued attention and exploration. The story of Venus is ultimately about perspective. From Earth, it appears as a brilliant point of light, the evening star, the morning star, beautiful and serene. But when you look closer, when you develop the technology to see through its veil, you discover a world of unimaginable hostility and alien beauty. That duality, the appearance versus the reality, reminds us that the universe often conceals truths that require effort, ingenuity, and persistence to uncover. NASA has finally shown us Venus's true face. Now the real work begins, understanding what that face is telling us about our place in the cosmos.